Hello everyone. Today I'm here to talk to you about the Rust in embedded critical systems and the journey that brought us from the innovation phase and is bringing us to the production phase at Infineon. So I'm going to present first this overview of our journey so far, and also how we did to identify the gaps that we were having or that we need to close to go to production phase, and how we did to close them and what are the next steps that we foresee. A little bit about myself. I am from Brazil actually, and happen to not be so good at football as many would believe. So that's why I pursued my master thesis in electronics engineering in Brazil, and I started my career at an electrical company there. And then I moved to Infineon 7 years ago, where I started as a firmware engineer. And since 2019, I discovered Rust through some colleagues at Infineon, and nowadays I am the facilitator of the Rust community inside Infineon, and I also promote the Augsburg Rust meetup in the city where I live in Germany today. And I'm also a husband of a lovely wife and a father of a young 8-year-old boy who loves to play ice hockey. And I'm also in general interested in innovation, sports, and board games. So if you have a tip for me, which would be a nice board game to bring from China to extend my board game collection, I would be happy to get it from you guys. And also my contacts, please. If you want to talk later on, please feel free to contact me. All right, enough about me. Let's talk about Rust. So how did we start it? We started with Rust back in 2019. We looked into this new interesting language that was around, that kind of looked good for embedded systems. And we used some opportunities like these hackathons, megathons that are available at Infineon to explore it and try out stuff. I believe if you're embedded engineers, you already had this nice feeling when you see finally a LED blinking that looks like it's so simple to many of other people that doesn't understand that meaning behind it, but we managed to do the first time this LED blinked with Rust code inside one of the Infineon chips. It was really a nice feeling. So we used back then the available documentation about embedded Rust, and we explored and in every new opportunity further steps like using Rust together with C as a library, creating a full Rust project, trying out in simulators, trying out in our emulators and chips and so on. And yeah, it took us long enough to say, okay, Rust can be used in our chips, at least as at first glance. We need to take a more serious step. And back then in 2021, then also Rust took a nice serious step, creating the Rust Foundation, showing, hey, Rust is a serious project, we will have it funded. And we thought, okay, then we can rely on this technology. And we created then the first innovation project inside Infineon to evaluate Rust in more deep sense, looking into our security controllers, things like the ARM custom data path extensions we evaluated. We also evaluated inline assembly that was then shortly stabilized in Rust. It was a really nice thing for us back then because we need inline assembly even when programming in high-level languages now and then. We evaluated the security compiler extensions, if we could do secure coding using Rust, and Rust in our multi-core devices we also tried, and we created the first informal Rust community inside Infineon where more people were trying to do something and said, hey, let's try to support each other inside Infineon to make it go further. And then we also promoted the language inside Infineon, doing some trainings showing that it was feasible to use in our devices and to get some momentum. And in 2023, then we finally started with the first pilot projects where at least some components were starting to be developed in Rust. Of course, for that, we had to create internal infrastructure to mirror, for example, Crates.io and other repositories online, so we could easily integrate in our CI environment to facilitate the tests. We created first some parsing projects like this certificate parser, and later on we also created a bytecode interpreter, and this bytecode interpreter is really interesting. We're thinking about making open source, or at least bring some people to work with it. You could think, yeah, we have WebAssembly, why you have a new bytecode interpreter? So the nice thing about this one is only 2 kilobytes of size. So we can, and it's scalable, so you can also create more instructions and so on, but it's another talk. Then we also created some examples with Infineon chips. So we started creating for Tegrion. Tegrion is our latest security device for payment and for ID. If you are a customer from Infineon, you get them in your SDK. Unfortunately, these kind of devices, they are not sold to anyone, let's say, and you need to sign an NDA and so on. So it's kind of limited as of now, but it's there. And we also have then the Aurix platform that already received a compiler, some examples they made from some partners from Infineon. And last year we also created the official Rust community, where we not only support each other, but we also define what will be the next steps of Rust inside Infineon, what should be done first. And that's where we came then this year to this point to evaluate the software process and say, hey, what are the gaps that we have that we need to fulfill to make it really going from this evaluation or innovation phase to production. And that's what we want to achieve then for the next steps, to go to a systematic rollout at Infineon to make the Rust the next de facto standard for embedded development. All right, so how we did this assessment. So we usually work on using this V model for critical systems, where we always start from the left side, having first to define the requirements, defining a specific architecture to cover these requirements, having a low-level design. We need to implement the code, and then you need to progressively test this code to make sure that it fits to the left side with the design, with the architecture, and the requirements. And everything needs to be traced, so to make sure that from the quality perspective, you are fulfilling all of the established requirements, and the product has the quality that you need to deliver to the customer or to the market. On the left side, as you see here, you can consider these 3 first steps like language agnostic to some extent. Of course, there are some aspects. If you look into, you see, you can spot some, oh, this is more like object-oriented architecture, this is more like imperative code, but in general, we saw, okay, this part here, we don't need to have anything special for Rust at first. The part of the coding here, we saw, okay, we have already a qualified compiler, so we have a compiler for Aurix. Now we have a qualified compiler for ARM from Faro Systems, and we already proved that it's suitable for embedded devices. And okay, there is still a gap here with regard to MCDC coverage, but we saw, okay, this is already being addressed from some players. Infineon is not a specialist in compiler technology. We will leave it to the experts, and we'll monitor it, and we continue where we can really support and where we can act. Then we started looking at the right side. So on the right side, we had to answer these 4 questions. So first of all, how do I get access to the hardware using Rust? How I can test these drivers that are accessing the hardware in a unit way, so isolated for the rest. from the rest of the components and still isolated from the hardware itself. The next phase, how can I test these device drivers in an isolated way, separated from the rest of my big project that's using these device drivers? And finally, when I have the tests, how can I make sure that these tests are covering the requirements that were established in the first place? Answering the first question. And here, many of you might say, hey, why are you discussing this when SVD2Rust are already around since a while? Well, we had some discussion internally, and we said, okay, we have our SVD2Rust, but there are some things that we happen to have a different view. So Infineon has already an industry expertise, and we were discussing about the undefined behaviors related to the hardware implementation. And we say, okay, this undefined behavior, when you talk about bare metal in development, it's a lot broader than memory safety alone. So when you interact with a special peripheral, it might be the case that it doesn't you cannot have a safe code, let's say, only interacting with one single register, because the side effects that it produces when, or it might produce when you interact with it, when you change the value, might affect some other peripheral eventually, or the state of a state machine inside your hardware. And then we decided, let's not call register access a safe code, let's maintain it unsafe to avoid any kind of confusion. Another part would be, we don't want to have ownership in the registers level, because that brings more problems than it solves. So that's a different view, and we saw the chip tool from Embassy project had the same view. We actually got inspired by that to create SVD2PAC, and that was our decision then. And we thought, okay, let the community write their own tool, and we as an industry partner, we write our alternative tool, but we make it open source as well. So the users can then in the end choose in the open source community, but Infineon then stick to this tool for its chip. And also what we wanted to have is a pack without dependencies to avoid any circular dependencies. So the peripheral access crate generated by SVD2PAC is then free of any other external dependencies. So this was the first an open source project that we created by my colleague Oresti Bernardi. He's the maintainer, and you can use, install, and contribute if you want. So, and we had one question: how are we going to test it now? Because we need it from Infineon side, and we need to make sure that the Infineon chips work well with this tool, but we also want to make it open source. And how can we make sure that? So should we block the eventual changes if something breaks our internal regression or usability? And after some discussions, we decided to do in two layers. So first layer of testing, it's only in GitHub, where we have a generic SVD that it doesn't contain any information specific from Infineon. So to make sure, okay, it will work. If you follow the SVD standard, it will work. And for the Infineon specific SVDs, then we have an internal layer of testing. And in case at this second level we have a problem later on, then we need to act as another usual user of the tool and file then issue a pull request to fix, and we need then to update the tests in GitHub. So the main base is really GitHub, and it should work with open standard from SVD, and it shouldn't contain anything that it should be specific from Infineon, and that's how it ran, how we handled now the tooling. The cargo deny, we bought it, and it was a discussion with our legal department. We wanted to keep all the dependencies and all the development only with permissive licenses, so that's why only these 4 licenses are allowed in SVD2PAC, even for the dependencies. All right, so now we had a way to access the hardware, and we wanted to have a way to test these accesses now using an approach that would not require to test with the final target hardware. And why is that? Because using the hardware will force you then to have a hardware in the loop infrastructure that is usually more costly to have. You have then limited resources to test, and it's also more expensive to maintain. So we wanted to have something that could abstract easily the access to the hardware, and you can also control the behavior during the tests in such a way that you can mimic the hardware, so you can make sure that your device driver or your hardware abstraction layer will perform the correct sequence of access to the hardware to perform its function. This was then the RegMock tool. It was developed in Graz in collaboration with the University of Graz. And it's already available, and it's a library that's integrated in SVD2Pack. So if you see here, you can use SVD2Pack, generating the pack with the flag features all, where you generate it for the target hardware, or you can have for the unit tests, where you use the flag tracing, and then it generates this logging part. Instead of accessing the addresses of the hardware to set the bits, it generates a log file, and this file can be accessed then by the unit tests through the asserts, and let you know test your hardware abstraction layer without the target in any kind of platform you have: Linux, Windows, Docker, VM, local. And that allowed us to speed up the development, or can allow us to speed up the development, have this short loop of checking for this kind of device drivers. But in the end, you also want to check if your hardware, or if your hardware abstraction layer works together with your hardware. Of course, that's part of the integration tests. So to do that, we wanted to have something that will do it in an automatic way, like we have in the unit test. So we looked into the available projects, and was already a nice project around from Faro Systems in a bigger project called Knurling. And inside this Knurling project, they had this deformat test. And this deformat test is something that already takes your library, it gets your library into a binary, gets the test that you wrote for your library and compiles it to the target and put it in a single binary, and you can flash it to your device. With that, you can control the flashing with OpenOCD. Here we used OpenOCD at first to flash it to the device, and we're using deformat and deformat test. We log these changes or these results from the tests, and we send it back to the PC which is controlling the test. But it allowed us to have then really out of the box the test framework for these device drivers. This was developed then in collaboration with the University of Augsburg, with Manuel Hatzel, the master student that worked on it. In the end, this project allows us to create these logging files for post-processing of the test results. Now, with the test results done, we need to have a way to trace it back to the requirements. And to do that, we need to have a way to say this test is corresponding to this requirement. And to do that, we created a new tool called Mantra. This is also from Manuel Hatzel from the University of Augsburg. And the idea here is that we have these prog macros that can be used either in the source code or in the test code, as you see here. And it will tell to Mantra, this tool, say, hey, this piece of code here is related to this other, to this specific requirement. Inside the brackets there, you can have any type of ID, and this ID then should match to the ID that you have in your baseline. So for Mantra to work, then you need these 3 input files, the covered schema, that's a JSON file that's coming from your test framework. In this case here, it came from embedded runner, but you can have any kind of embedded framework as long as you generate this type of file, so you can convert it yourself. And we will need to have a requirements baseline that's also a JSON file that you can generate yourself, or have an export for Jira, Jama, or some other tool and convert to this format, and also a way to have manual reviews of the requirements. These three inputs, they are collected by Mantra. It generates a database, a local database, and you can have a test report generated from it. And in this test report, you can also control its layout as you like using a Terra template. And this is nice because with this test report, then you can hand it over to your quality manager and say, hey, here it's my test. I tested my library for this specific device. This test is covered, this requirement is covered by this specific test. As you see here, this test was executed, and the execution of this test is passed. Everything was tracked here by this tool, and then you can generate the final output for that. With that, we covered all these four topics that I mentioned, but there was one topic that was still missing that we did not identify right in the beginning, but during the process of these implementations. And this was the test documentation itself. It means right in the beginning, you need to have a document that you say how you're going to test your device. And this is an input to your process. And as of now, Rust has a really good way to generate test documentation from your code, and you can see it in the Docker S. It's really nice to navigate, and out of the box works perfectly. But if you have a documentation for your test, it doesn't appear anywhere. And then we looked into it, and my friends Luca, Heike, and Francois from Infineon, we got some time to look into it from Infineon, and we said, hey, it's not that easy to fix that. And we finally managed to make it work in a fork that we did from Rust at Infineon. And we now have a pull request open. And with that, you can generate, as you see here, from the same way you have the documentation written for a function, you can have a test documented, and you can even include these requirements that we have for Mantra and need to Mantra. And it will appear in the same way that you're used to for normal source code. So, and with this cargo doc -- document test, then you will have this feature. And then we're now working together with the community and for the project maintainers to get it done. Yeah, so with that, then we are pretty confident that we covered the most important parts of the software development framework that we are using to have the necessary artifacts to fulfill the quality artifacts required. But of course, there are still some open gaps that are nice to be fulfilled, like automatic generation of block diagrams from your source code would be really nice to have in terms of review and compare to the input design, for example. This is one gap that we are looking into to close, and this is what we want to proceed now, to be closer to the community and to interact more with the project to continue closing the gaps and improving. Of course, the tools that I presented here, they are in an early stage. They are already functional, you can use. We are using it in Infineon, but we want to extend and improve them in terms of documentation, testing, and training, and you are all welcome also to contribute to the tools to improve them. We still don't have a centralized open source project that uses all these tools at once. Each tool has its own examples, but it's important to have one single place to look into how a template project will look like when using those. We are working on it, and we're going to make it available soon as well. One other thing that we were discussing, okay, now we have the basic tools to start developing. Now we need to have the same infrastructure or the same ground base to develop embedded systems for security and safety in the right way, let's say. So we need some design patterns, and we need some coding guidelines, and that's independent of the Rust features. we will have eventually to have that. So Infineon is already participating in some discussions about it, and might be the case that in future we will see something like a Manczak-Rust or a SIRT-Rust, because although we have the memory safety at Rust, there are some other aspects of the software development that needs to be addressed by this kind of code guidelines. And of course, there is also about the topic about productivity. We are looking into that as well, that Rust might help us close this gap that exists between hardware development and software development. And with these features that Rust has, like the type system and zero cost abstractions and so on, we see that we could close this gap, or make this bridge a lot smaller between these two worlds. And that's what we are looking into, and we believe we can make it even easier to write code for embedded systems using Rust. That's it. I hope you liked the presentation, and I hope I got you interested in using and contributing to the tools. Please contact me if you have any questions or remarks. Wish you a nice day and enjoy the rest of the conference.